Okay, so today we are having our tutorial 2. All right, where we will be going through the concepts on the capacitors and inductors. Okay, so bringing back with the concepts we covered in the recent studios. Okay, then on Thursday we have one more session, which is a revision session for your midterm this Saturday. Okay, so we'll talk about the midterm, I think, more on Thursday. So today we'll just focus on the tutorial. Okay, so I hope you all have tried. Okay, the questions. Okay, so let's get started. Okay, the rest maybe we'll join in later. Okay. Okay, so as before, I will not go through all the theory part again because it's the same material as your handout. All right, but as we go through the questions, you'll be able to recap those concepts and those theoretical elements that will help us to solve these questions. Okay, so the first question. Okay, the first question, we are given a DC source. All right, with this circuit where we have a resistor, two resistors, a capacitor, and inductor. Okay, find the energy stored in the capacitor and the inductor. All right. So what we want to understand is what is the or how the circuit behaves in a steady state. All right. So basically, what we know is for steady state. Okay. So once we reach steady state, okay, two things. Okay, capacitor is considered open circuit, and inductor is considered as a short circuit. All right. So technically, if I were to redraw this circuit, okay, I got 6 volt here, 2 ohm. So the capacitor here becomes open circuit, and the inductor is a short circuit, and I have this. All right, so this is basically your VC, and this is your sort of IL, the current through the inductor, and the voltage across the capacitor. And this IL is actually the same current that comes out of the source and goes through both the 2 ohm and 4 ohm resistor. All right, so basically, if you look at it in steady state, you only have a simple series circuit. All right, which means that I can calculate my current I as 6 volt divided by 6 ohm. Okay, 6 ohm is because 2 and 4 are in series, which will give me 1 ampere. All right, and the VC, okay, so the voltage across the capacitor can be calculated as the voltage across the 4 ohm resistor, because both of them are considered parallel. Right, they're both parallel, so it's the same. So the voltage across the 4 ohm resistor is I times R, which is 1 times 4, which is 4 volt. Okay, and the current through the inductor, IL, is the same as I. Okay, the same current that flows through the inductor. So once I know this VC and I know IL, I can compute the energy. Okay, because for energy formula, all right, they are both related to the two different parameters here. Okay, so for the capacitor, okay, the energy stored in the capacitor is half CV squared, which will be half times 2 micro times 4 squared, which will give me 16 microjoules. And the energy across the inductor is half Li squared, which is half times 2 milli times 1 square, which will be 1 millijoule. All right, so that is basically the way you analyze this circuit. All right, so you're just trying to make sure you understand the behavior of the capacitor and inductor in steady state. Okay, so I think should be okay. Okay, so as before, I will just continue, all right, through the questions Okay, and if you have anything that you're not sure, feel free to ask, all right, either in the chat or you can unmute and ask. Okay, so there's a question, are there voltage across inductor? All right, so for inductor in steady state is considered short circuit. For a short circuit pathway, the voltage is 0. All right, if you look at the Ohm's law, correct, V is equals to IR, correct. So if I have a short circuit, the resistance is 0. So by Ohm's law, if I have a short circuit path, the voltage drop across any short circuit path is also considered 0. Okay, so let's move on. Question 2. So in question 2, the switch was closed for a long time before t equals to 0. At time t equals to 0, the switch is open. Determine the value of the capacitance needed so that the voltage V1K will remain greater than equals to 9 volts for 2 seconds after the switch is open. Okay, so basically you need to analyze it. So it's quite standard. The process is quite standard. Okay, whenever you have a circuit like this where there is some switch and then at time t equals 0, you open it or you close it, whatever, then we analyze in 3 stages. Okay, what happens at time t equals to 0 minus? Okay, so 0 minus means the time just before the event. So in this case, the event is the switch being open. So prior to t equals to 0, it was closed for a long time, which means that the capacitor is already at steady state. Okay, so we can say that the capacitor is at steady state. Okay, which also means that capacitor is open circuit. Okay, so at steady state, at t equals to 0 minus, the capacitor is sort of open circuit. Okay, and we have achieved steady state in the circuit. So at t equals to 0, okay, so before that, since capacitor is considered open circuit, okay, that means you have to redraw the circuit. 20 volt here, 1K here. So this is how the circuit will look like. Okay, so this is your VC and this is your V1K. All right. So since the capacitor is open circuit, okay, the VC is equals to the V1K. Okay, and since this first resistor is 1K and this resistor is also 1K, and it's a series circuit, we can say that it's a simple voltage divider rule, so that will be 10 volts. All right, so that is basically how the circuit is just before I open the switch. Okay, now at t equals to 0 plus. Okay, so one of the things, again, as we discussed in the studio, is the voltage across the capacitor and the current through the inductor cannot change instantaneously. Okay, which means that whatever was the sort of situation or condition at t0 plus is the same situation you will be at 0 minus, with the same situation will be in 0 plus. Okay, so at 0 minus, if I was at 10 volts, at 0 plus, at the very initial point where I flip the switch, it is also going to be the same. That means VC is still going to be 10 volt. Okay, now the last thing that we also need to analyze is at t equals to infinity. So at t equals to infinity, what happens? So now what happens is the switch is open. So when the switch is open, what happens? The circuit that I have is basically a capacitor in series with a 1K ohm resistor. Okay, because the left hand side, the switch is open, so there is no current flowing in the bright. So all I have is this. Okay, so by by the studio, you know that once I have a capacitor that is charged and I put it in a closed loop, it starts to discharge until there is no more charge left. Correct? Like how you saw the LED, correct? When you flip the switch, it lights up, but then it dims until it totally goes off. Correct? So that's the same thing that will happen. That means the current will flow as the capacitor discharges until there is no more charge left. So when there's no more charge left, means we know that at time t equals to infinity, it will be 0 volt. Okay, so these are sort of the standard steps that you need to do. Okay, every time you have a circuit like this. What is a 0 minus? What is a 0 plus? And what is an infinity? Okay, and once you know this, you can put it into your standard equation. Okay, the transient response equation. So that equation is what? That equation is VC t is equals to VC0 e to the minus t over tau plus VC infinity 1 minus e to the minus t over tau. Okay, where in this case tau is RC. All right. So we know that at t equals to infinity, we go to 0 volt. So which means that this is 0. Correct. And since that is 0, we can ignore that part of the circuit. And so we just focus on this part of the circuit here, which is VC0 e to the minus t over tau, which will be 10 e to the minus t over tau. So that is the expression for the voltage across the capacitor. All right, so that is the expression. So we are basically working towards this expression, this final expression that relates the transient behavior of the capacitor over time. Okay, once the switch is open. Okay, so now that we have this equation, we come back to what are we trying to solve. Okay, we want to solve for this. What capacitance is needed such that it remains greater than equal to 9 volt for 2 seconds. Okay, so we know that the discharge, okay, the discharge is basically going to go from 10 volts all the way down, right? So if I were to draw the graph, okay, it will go something like this. Okay, so it will start off with 10 volts, okay, and then it will go. So what I want is, I want to see, or I want to ensure that at time t equals to 2 seconds. 2 seconds, this value is greater than or equal to 9. Okay, that is what I want to achieve. All right, so of course this is related to the time constant. Okay, since the resistor is already fixed, what we want is to find the capacitance that will allow me to fulfill this requirement. All right, so what I want is that VC at time t equals to 2 must be greater than equal to 9. So I just substitute this inside, correct? So I just say that 10 e to the minus t over tau must be greater than equal to 9, and then you solve. Okay, solve for this. All right, so when you solve for this, what you will get is, okay, so the solving part I think should be okay for all of you, correct? You just take the natural log of both sides, okay, then you just move things around. Eventually what you will get is this tau must be greater than equals to 19 seconds. Okay, which means that RC must be greater than equal to 19 seconds. Okay, and since your R is fixed, so C must be greater than equals to 19 over 1K. So C must be greater than equals to 19 millifarad. Yeah, the 95 seconds, yeah, we're coming to that bit first. Okay, so this is the first one over here, okay, where we're calculating the C. So this value of C is to satisfy this first question here. Okay, that means what is the value of C to make sure that the voltage remains greater than equals to 9 volts for 2 seconds after the switch is open. Okay, so that is the final answer here for the first part. Okay, so the next part is what is the energy stored? Okay, so this is straightforward. Correct, energy is half CV square. Okay, it should be half. So since we know it's 19 milli times V, so it's 10 square to 0.95 joule. All right. Now the last part is get and dimension the capacitor's voltage versus time. So this is again the same graph that we draw just now. Okay, so we know that the way that the capacitor will discharge will be like this. Okay, okay, and we will start off with 10. All right, so we know that the tau in this case is 19. Okay, tau is RC is 19 seconds. So at 19 seconds, it falls to 36.8%. Okay, of start value or original value. All right, so and tau equals to 19 points. Maybe it's on here. Okay, you fall to 3.68 volt. Okay, at 5 tau. Okay, at 5 tau, it should be 5 times 19, 95 seconds. It is where it is almost close to zero. Okay, 99 point something percent or something. Okay, you can look back at your slides there. Okay, so that 5 tau is where it is almost fully discharged. That is, by 95 seconds, you can say that it's almost fully discharged. All right, so the 1 tau is where it falls to 36.8% of the initial value, and 5 tau is where it is almost fully discharged. Okay, so that is how you sort of draw this response. Okay, so I think that is clear. Let's continue. Okay, so question 3. The switch was closed for a long time. Before t equals 0, time equals the switch is open. Determine the energy that was stored in the inductor at time t equals to 0 minus. Okay, so the same analysis. Okay, so first we say at t equals to 0 minus. So it was closed for a long time. So if it's closed for a long time, then what happens? That means this inductor behaves as short circuit. So inductor is short circuit because at steady state inductor is short circuit. Okay, that means your circuit, okay, is now reduced to just 5 ohm and this. Okay, so always remember, whenever there is a short circuit part, you will always take the short circuit part if it is parallel to any other branch with any other component. All right, because the short circuit will automatically override anything else that is connected parallel to that short circuit line. Okay, so because of this short circuit line, nothing will go through the 5K resistor. Okay, which means that the current, okay, through the inductor, which is this, is actually 10 over 5, which is 2 ampere. Okay, so the energy will be half Li square, which will give me 2 millijoules. Is it possible for Thevenin's analysis across inductors? I mean, across inductors or capacitors, you can still derive the Thevenin equivalent. all right, and you will need to do that if your capacitors sort of charging or discharging is through some network of resistors, correct? Because the time constant, correct, RC or L by R, the capacitor, you know, correct, but the resistor is based on a single resistor, correct? But if you have multiple resistors that are connected, then it is equivalent to looking at it from a Thevenin's equivalent to know what is the effective resistance that you are discharging your capacitor inductor through. Okay, I think later there is one question on the Thevenin's equivalent, correct, with capacitor, then we can look at that. Okay, so for part B, determine the voltage across the 5 kΩ resistor at time t equals 0 and time equals 0 plus. Okay, so at time t equals to 0 minus, we know that the inductor is already a short circuit. So since it is a short circuit, voltage across any short circuit path will always be 0 volt. Okay, now how about at time t equals to 0 plus? Okay, so at time t equals to 0 plus, okay, what is the voltage across the 5K? Okay, so how do we look at this? All right, so the way to look at this is when the switch is open. Okay, so basically what you have is you have this inductor here. Okay, and you have this 5K ohm resistor. Okay, so I have this 5K ohm resistor V5K plus or minus. So we know that when the circuit was at steady state, the current that was flowing through the circuit was in this direction. Okay, in this direction. It was going through the inductor from the top to the bottom. Okay, so when I flip the switch, okay, just like we said, the current through the inductor cannot change instantaneously. All right, that means whatever current that was flowing through at that time, okay, would be the same current that will also be flowing through, okay, at the time when I just flip the switch. Okay, so when I flip the switch, all right, the current that was flowing through the inductor is now going to go in this direction upwards here. All right, so it's now going to go in this sort of anti-clockwise direction. Okay, so what is the current? Okay, the current that we know is 2 ampere, correct? So just now we know that the current, okay, that we calculated is 2 ampere. Okay, so that is the current that was flowing through the inductor at this time. So now the same 2 ampere current is now going to flow through this 5K ohm resistor in this direction, in the direction from bottom to up. Okay, so in terms of voltage, we can say that it is I times R. That means it is 10 kilovolt, correct? IR. Okay, but because of the way it is labeled, correct? That means the labeling of this 5K is such that the positive is on top and negative is below. which means that rightfully, if I label it, that means if I were to label it this way, then I can say V5K is 10 kilovolt. Correct? Because that is in alignment with how the current is flowing. Okay, from the higher potential to lower potential. Okay, but because I have already put plus and minus in the opposite direction, which means that this is actually negative 10 kilovolt. Okay, so it's always I think we have seen this before in the last tutorial as well. So if we never put a plus and minus, then you just can state that this is the direction and this is the voltage. Okay, in this direction. But if there's already a plus and minus, then the answer should be with respect to the label that is already provided. So as long as the current is flowing in that same convention, that means if it is going from plus to minus, then the voltage drop is considered positive. Okay, but in this case, the current flow is against the voltage drop. So we consider the voltage drop as negative. Okay, so that is why the answer is negative 10 kilovolt here. Okay, and the last part here is the time constant. Okay, so time constant is quite straightforward, L by R, which is 1 milli over 5K, which would be 0.2 microsecond. Okay, so that is this question here. Okay, so we can go on to question 4. So question 4, again, RC circuit. So the switch was closed for a long time before t equals 0. Okay, so current measured by ammeter is 1 ampere at t equals to 0 minus. Okay, at t equals 0, switch is open. What is the value of the unknown voltage? All right, so we will do the same analysis, correct? So first thing is at time t equals to 0 minus, we say that the capacitor is steady state, which means that the capacitor is open circuit. So if the capacitor is open circuit, then effectively there is no current flowing in the branch. So you have this, you have the ammeter, so you have 12, you have your 12 ohm, you have your 6 ohm, and this is your V. Okay, so the capacitor here is considered open circuit. Okay, and what we know is at steady state, this current here is 1 ampere. So since we know the current is 1 ampere, the voltage drop across both the components would be 12 plus 6 times 1, which will be 18 volt. So since it's a simple series circuit, that also implies that your V is actually 18 volt. Okay, so that part I think should be okay. Now the next part is, what is the ammeter's reading at time t equals to 0 plus? Okay, so at time t equals to 0 plus, what happens? So at time t equals to 0 plus, okay, I basically at time t equals 0, I open the switch. Okay, so once I open the switch, all right, the current, there is no more current flowing through the 6 ohm resistor. All right, but since the voltage, I mean the 6 ohm resistor and the capacitor are parallel, that means they both have the same voltage. Correct? VC is the same as the voltage of a 6 ohm resistor. Okay, so we can say that VC is the voltage across the 6 ohm resistor. So by a simple voltage divider rule, you get 6 volts. Okay, so we know that when I flip the switch, the voltage across the capacitor is 6 volt. Okay, so if I were to redraw it now, so what I have is I have 18 volt here, I have a 12 ohm resistor, I have an emitter here, and I have another capacitor, and this capacitor is 6 volt. All right, so the current that is flowing through would be again based on Ohm's law. Correct, that means the voltage difference across the resistor divided by the resistance. So the I would be 18 minus 6 over 12. It should be 1 ampere. Okay, so that is the current that will be flowing through the emitter at time t equals to 0 plus when I first flip the switch. Okay, and the last part here is the emitters reading at time t equals to 12 seconds. Okay, so at time t equals to 12 seconds. So this comes back to the formula, right? The full transient formula. So VCT, okay, so again VC0 e to the minus t over tau plus VC infinity 1 minus e to the minus t over tau. Okay, so now the first thing is VC0. So we know that VC0 is 6 volt. Okay, that means when I first flip the switch, VC0 is 6 volt. Okay, now when I leave the circuit as it is after I flip the switch, what will happen? Okay, so we know that the current is flowing this way and into the capacitor, which means it is effectively charging up the capacitor until a point of time where both the voltages would be the same. All right, and then it will no longer have any current flow because again it reached steady state. Okay, so VC infinity would be the 18 volt. Okay, so this is in a sense similar to like the dual battery. Okay, when we had the two parallel battery. Okay, when one voltage is higher than other voltage, what happened? The current will flow in one direction until they both stabilize. Correct. So it's the same concept, but in this case, since it is a voltage source, which means that the voltage here is fixed. Correct. It's not a battery that is discharging. It's a fixed voltage source. That means that I will continue to supply current to the circuit until a point of time where the capacitor becomes fully charged. Okay, so VC infinity will be 18 volt. Okay, with that you can sort of rewrite this equation minus T by tau plus 18 tau. Okay, and then the rest is substituting it based on the value. So VC at time 12. So you substitute T equals to 12. Okay, then you do all the calculation, you should get 13.585 volt. Okay, so that is at 12 seconds, you get this voltage. So the current at that time is again Ohm's law, right? 18 minus 13.585 over 12 ohm, which will give me 0.368 ampere. Okay, so let's move on to the next. Okay, so we have this circuit here. and we are told that at time t equals 0, S1 was closed. Okay, before t equals 0, S1 was closed and S2 was open for a long time. And then at t equals 0, both switches are flipped. Okay, so let's do this step by step. So the first thing is at t equals to 0 minus. All right, that means just before it is flipped. Okay, so just before it is flipped, since it is in the position for a long time, that means S1 was closed for a long time, which means that the inductor is short circuit, it's in steady state, so it's short circuit. All right, and S2 is open. All right, so that part of the circuit, the 50 ohm, we can ignore for now. All right, so the first instance of the circuit will look like this. Okay, the switch is here. And this is the inductor as a short circuit. Okay, that is basically what you get. Okay, so they want to find the current IT after t equals 0. So first I need to find out the current IT at t equals to 0 minus, correct? That means before flipping the switches, what was the current flowing through here? Okay, what was this IL? Okay, so this is basically nothing more than a simple DC circuit, correct? So if you look at it, the total current over this circuit through this circuit is 30 over 20 plus 20 parallel to 20. Okay, so that will be that total current that comes out. Okay, so I'll call this I. All right, and then IL would be a voltage divider, sorry, a current divider rule. So 20 over 20 plus 20 multiplied by I. That would be IL. Correct. And so if you solve everything, you will get the answer as 0.5 ampere. So that is IL. So this is the current that is flowing through the inductor just before the switches are flipped. Okay. Now, what happens after I switch? Okay, or I flip the switches. So once I flip the switches, so this part of the circuit, 20 ohm, 20 ohm, 20 ohm, I can ignore because it is already open circuit there. All right. And what we're interested in is, so whatever current that is flowing through the inductor is only going to go through the 50 ohm and 50 ohm resistor. Okay, so if I were to draw the circuit, okay, at t equals to 0 plus, so the circuit will look like this. It's just this plus this and this. Okay, so you have your 1 millihenry inductor. This is a 50 ohm and this is a 50 ohm, and we know that 0.5 ampere is flowing in this direction. Okay, so to find the expression for the current, okay, we can say that this would be, again, the expression would be IT I0 e to the minus t over tau plus I infinity 1 minus e to the minus t over tau. Now, so for this circuit, what is your tau? Okay, your tau is L by R. But what is your R? So this is again the sort of application of the Thevenin's equivalent, correct? Why? Because in this case, you have an inductor, but the inductor is sort of discharging through more than one resistor, right? So I need to find the Thevenin's resistance, that means the equivalent Thevenin's resistance, or how this current is going to discharge. Okay, so if you apply the Thevenin's equivalent, then it looks like this, correct? That means I imagine that I open circuit here, then I have two resistors here, which is 50 and 50. Correct. So if I would imagine that this is a imaginary source, then the current would split through 50 and 50. Okay, so the Thevenin's resistance or equivalent will be 50 parallel with 50. Okay, so the time constant here would be 1 milli over 50 parallel with 50. Okay, that is how you calculate the time constant for this. All right, now coming back to this expression, we know that the I0 is 0.5 ampere and I infinity is, if I leave this circuit as it is, again, as the inductor discharges all this current, it will eventually go to 0. Okay, so the only expression or only part left is your I0, which is 0.5 e to the minus t over tau. So that is the sort of expression for the current through the inductor. Okay, so you can move on to question 6 here. The switch was open for a long time before t equals 0. At t equals 0, the switch is closed. What the voltage at time t equals 0 plus? Okay, so the current through the inductor. Okay, so at t equals to 0 minus, okay, the switch is open for a long time, which means that the current RL is equals to 0. Okay, and at t equals 0 plus, when I first close the switch, again the current will initially also be 0. Okay, and since the current is 0, okay, at time t equals to 0 plus, then we can also say that the VAB at t equals to 0 plus will also be equals to 0. Okay, again, this comes back to the principle of the current through the inductor not being able to change instantaneously. All right, so whatever current that was flowing in prior to the switch event is the same current that will flow through when I initially close the switch. So when I initially close the switch, it will still be 0. Okay, so that is why the VAB, okay, at time t equals to 0 plus will be 0. Okay, then the next part is, what is the IR at time t equals to 1 millisecond? Okay, so to find the current, okay, so the current direction, again, it is based on the supply. So in this case, the supply is pointed this way, means the current will flow this way. Okay, so the next part is asking us what is the what's the current at time t equals to 1 millisecond. Okay, so let's look at this. So to find this, we need to understand how the circuit is going to behave once I close the circuit, once I flip the switch. Okay, so once I flip the switch, okay, then of course current starts to flow through the inductor. Here what we can do is, all right, we can simplify the circuit a bit, okay, in a sense that you see that when the current flows, there are two parallel resistors, 10 ohm and 10 kilo ohm. All right, and if you try to calculate 10 parallel with 10K, you will see that it's approximately 10 ohm. Okay, whenever you have a very small, I mean, we know that when resistors are in parallel, the effective resistance will always be smaller than the smallest resistance, correct? So eventually it will be very, very close to 10, okay, when I combine this. Okay, so I can sort of simplify this to say that the circuit will look something like this. Okay, 10 millihenry and 10 ohm. And this is the VAB. Okay, so with that, I can find the expression for the current, which will be again IL0 e to the minus t over tau plus IL infinity 1 minus e to the minus t tau. Okay, and since IL0 is 0, so this one is 0, so that part is no longer there. And IL infinity is, again, what is the final current? Final current is when it's steady state, your inductor behaves as a short circuit, so the current is 10 volt divided by 10 ohm, which is 1. Right, so it's basically 1 minus e to the minus t over tau. So this one is actually 1. Okay, 1 ampere. Okay, so that is the expression for the current at time, at any particular time, and you just substitute the value here. So it is 1 millisecond. Okay, so you substitute at t equals to 1 millisecond, you get the answer 0.632 ampere. Okay, so that sort of wraps up the DC analysis part. Okay, so far what we'll be looking at is the DC analysis. Okay, so when we talk about DC analysis with capacitors and inductors, we are interested in the transient and in the steady state, okay, response of the circuit. Okay, so question 7 onwards is all on the AC analysis. Okay, so in AC analysis, basically we are going to deal with complex numbers and the phases and everything. Okay, I think most, I mean, when I walk around the lab, most of your calculators are quite, I think, quite advanced. All right, so if you know how to use a calculator to do all this conversion for you, very quickly, then I think you'll save a lot of time in the midterm. Correct? Okay, so if your calculator can do whatever you can do, then just go ahead and use it. All right. All our assessments are MCQ. Right? So you don't need to show any working for this. As long as you know the calculator is giving you the correct answer based on what you key in, then you can straight away use that answer. Okay, so I'll spend some time. All right, try to figure out all the things that the calculator can do. All right, so that you can save time doing the assessment. Okay, so coming back to the questions. So in terms of AC analysis, all right, the main idea is you want to convert the sort of time domain relationship between the AC source and the resistor, capacitor, inductor to, in a sense, the phasor domain, correct? And by doing that, okay, what happens is once we represent everything in phasors, then we are able to solve the circuit as how we solve a normal DC circuit. Okay, if not, what you have is in a time domain expression, you have all your differential equations and everything, which is very tedious to solve. Okay, so by converting them to phasors, then you are able to immediately use your DC analysis techniques and solve the circuit. Okay, that is why the complex number part comes in. All right, so even though that conversion to and fro is tedious, but actually it saves us a lot of hassle in not having to deal with differential equations. Okay, so in this case, we want to solve for the expression for VR. Okay, so again, if you think of this as a DC circuit, okay, that means if I were to redraw this as a DC circuit, where you have R here, and you have another component here. So in this case, the inductor, I call it ZL. Okay, so if you imagine all of this as a DC circuit, then VR is nothing more than a voltage divider rule. Okay, but in order for me to apply that very simple voltage divider rule, I need to convert it. Okay, I need to go through the process of converting it. Okay, so the Vs, okay, again will become a phasor. So it'll be Vm angle theta. Same thing here will be Vr angle theta, and this will be this will have a, okay, so before the Vr, okay, R is already expressed as it is, okay, and or what you want to find, and ZL is basically the impedance, all right, in the that is sort of equivalent to the resistance, okay, when we convert to phasor. Okay, so what we need to do is we need to make sure that each of the components are expressed in phasor form. Okay, so for R, there is nothing to do. For the source, we just take note of the magnitude and if there's any phase angle. So in this case, if there's no phase angle, then we can straight away write it as the angle 0 degrees. So this will be 10 angle 0 degrees. Okay. For inductor capacitor, you follow the formulas given to you. So for ZL will be J omega L. Okay. So the first thing is, what is omega? So our expressions here are always given in the form of cosine, okay, omega t. Okay, so we know that omega in this case is 10 to the power of 4. Okay, omega is 10 to the power of 4. All right, so this expression here, so this total impedance, all right, is given as R plus ZL. Okay, so the expression for VR is nothing more than a voltage divider rule, R plus ZL multiplied by your Vs. Okay, so if I put everything in the phasor form, what I'll get is R for R plus J omega L, and this is your Vm angle 0 degrees. Okay, so this okay, so for this first question, we will go through it so step by step just to make sure that you're clear. Subsequently, we can skip all the complex part. All right, and just understand the concept. So if I were to do this again, what you have is R Vm angle 0 degrees over. So you have sort of a polar form there, but you have a rectangular form in the denominator. Okay, so you need to convert the denominator to also polar form. So you have R square plus omega square L square square root and inverse tangent of omega L by R. So all these are the same formulas, okay, in your handout and that you used in your studio as well. All right, so with that, you can find, or you can put the final expression for VRT as R Vm R square plus omega square L square and cosine of omega t minus theta. Okay, and what is theta? Theta is this. So this is your angle. Okay, so theta is given as, okay, or basically how we do it is tangent theta is omega L by R. So theta is inverse tangent of omega L by R. Okay, so this is just just to make sure that you understand all the complex number concepts correctly. Okay, so the total phase angle is, again, the numerator is 0, so 0 minus theta, so that's why you have the minus theta here. Okay, the omega t is the original omega t that is already from the source. Okay, so what they next ask us to do is, what is the R that will cause the phase to be 45 degrees? Okay, so we know that the tangent theta, which is the phase angle, is omega L by R. Okay, so I want the phase angle to be 45 degrees. All right, that means this will be tangent 45 degrees will be omega, sorry, W omega L by R, and tangent 45 degrees is actually 1. So omega L is equals to R. So R is, substitute the omega L, you'll get 10 ohms. Okay, so when R is 10 ohms, then you get a phase difference between Vs and Vr to be 45 degrees. Okay, and the last part here is draw the phasor diagram. Okay, so the phasor diagram is, so we already have the expression for Vr, okay, from just now. So Vr, we already know it is Vm, RVm angle 0 degrees over R square plus omega square L square angle 45 degrees. Okay, so you substitute all the numbers inside. So 10 times 10 10 square plus 10 to the power 8 to the power minus 6. Okay, so this is what you will get. Okay, so that is for VR. Now for VL, okay, for VL is the same thing. Okay, it's the same voltage divider rule. So it just as here, just like if I wanted VR, I take R over R plus ZL. If I want VL, I take ZL over R plus ZL. Right, just like a same voltage divider rule as you would do with two resistors. So it will be ZL over R plus ZL multiplied by Vs. Okay, so that will be omega L angle 90 degrees over, again the same thing, 10 square plus 10, 8, 10 minus 6. Okay, multiplied by Vm angle 0 degrees, and this angle is 45 degrees. So that will give me 7.07 angle 45 degrees. Okay, so if you were to draw it, again, it's I think similar to your studio. Okay, so your Vs has no phase angle. Okay, so this is your Vs, and your VL is VL is 7.07 45 degrees, and your VR would be this way. All right. So this is again just to make sure that you understand all the sort of concepts about how to use the complex numbers correctly. Okay. So of course the complex number part is the tedious part, and like I said, if you use your calculator and try to figure out any easy shortcut that your calculator has, then I think that would be helpful. Okay. Okay, so let's go on to the next question, question 8. So question 8, find the current using phasors and impedance. So in this case, so it's the same concept, right? So if I want to find current, I is V by Z. All right, so I know what is V, okay, which is the voltage source here. I need to find what is Z. Z is the total impedance. Okay, so since R is given here, so what I need to do is convert this into its impedance, which is ZC, which is 1 over J omega C. Okay, so it will be minus J 1000 ohm. Okay, so what is omega? Omega is 10 to the power of 4. C is 0.1 micro. Okay, why minus J? Because 1 over J. Okay, so if you look at the complex numbers, 1 over J is minus J. Is the same. Okay, so your capacitor, the impedance is equivalent to minus J 1000. Your resistor is 1000. So the combined impedance here, okay, which is R plus ZC will be equals to 1000 minus J 1000 ohm. Okay, so that is the total impedance. All right, so putting that back into this expression here, you will say that I is equals to V, which is 10 angle 0 degrees over 1000 minus J 1000. Okay, it's basically V by Z. All right, then you just need to convert that into the Phasor notation. Okay, so you'll get 1000 root 2 minus 45 degrees, and then that will give me 7.07 45 degrees. Okay, so the expression, okay, in the time domain would be 7.07 times 10 to the power of minus 3 cosine 10 to the power of 4 t plus 45 degrees. Okay, so you can see that we are applying the same concepts, okay, as your Ohm's law, KVL, and so on. All right, only thing is it's just more tedious now because we have to deal with phases. Okay, so there's all this conversion going on. Okay, but other than that, it's exactly the same. Okay, exactly the same. Okay, so find the RMS value of the current drawn from the AC source. Okay, find RMS value of the current drawn from the AC source. Okay, so it is the same thing again. So I is V by Z. So I know what is my V. Okay, it's 230 volt RMS with 50 hertz. So I need to find Z, the total impedance. Correct. So the total impedance would be basically this resistor 10 ohm plus the combined resistance of 100 parallel with my in this case this would be become my ZL. So what is ZL? So ZL is J omega L. Okay, so J. So what is omega? So in this case, omega is not explicitly given, okay, because you don't give the expression, but you know that it's 50 hertz here, the F. So it will be 2 pi 50 multiplied by L, 100 milli. Okay, so that will give me J of 31.4. Okay, so that is your ZL. So now that I know ZL, I can compute my total ZT, the total impedance. So ZT will be 10 plus 100 parallel with J3 31.4. So you do the same thing as how you would normally do for parallel resistors. Okay, so if two parallel resistors means you multiply, divide by the addition. Right, so it will be 100 multiplied by J 31.4 over 100 plus J 31.4. Okay, then the rest is the maths part. So 18.98 plus J 28.59. Okay, so that is the expression for ZT, and then putting it back into this expression, you will get I is equals to B by ZT, which will be 230 over 18.98 plus J 28.59. All right. So since it is a division, you can convert it here. So you get 6.7 angle negative 56.4 degrees. Okay, so the current, actual current is this. So the IRMS current is 6.7 ampere. Okay, so again, this since it is already given as RMS. Okay, so when I use the voltage as RMS, the current is also RMS. Okay, so if they have given it as peak, then if you calculate everything, then what you would have gotten is the peak. Then you have to convert. Okay, so in this case, since they already gave it as RMS, then I just use the RMS value. So the answer is also RMS. Okay, so when you express it as the phasor form, the magnitude is the actual magnitude. Okay, so you don't need to convert it to any other form. So this magnitude that you get over here is the actual magnitude. So this is just the angle. So in this case, if they never ask for the angle, then you just give the magnitude as it is. Okay, question 10, Thevenin's equivalent. So again, this is same concept. So if this was a DC circuit, the Thevenin's equivalent is the same thing, right? That means to find VTH is the open circuit. So since A and B is already open circuit, this is again, just imagine that it is like this, correct? Okay, Z1, Z2. Okay, so if I were to look here and I say VTH would be Z2 over Z1 plus Z2 multiplied by B. Why? Because this is the open circuit voltage. So the open circuit voltage, this is just a voltage divider rule. So the same way you look at it as a DC circuit, you look at it in the AC circuit. Okay, so in this case, what you will get is VTH as, so this branch here will be 8. So in this case, they already given you the actual impedance. Okay, they never give you the inductance value and capacitance value. They already calculate your ZL and ZC. So it's a bit easier. So 8 plus J8 over 8 plus J8 minus J8. Okay, so that is Z2 over Z1 plus Z2 multiplied by the this over here minus 30 degrees. Okay, then you have 1 plus J. Okay, so the rest is again since multiply between rectangular and a polar form, you again convert. Okay, so the rest is, I would say, mostly just the maths part. Okay, the critical part is just making sure you understand to sort of apply the concepts correctly. Okay, so that is your VTH. Okay, then your ZTH is the same thing. All right, if you remember ZTH, what we say is we short circuit the source Correct. And we imagine that I place a supply here. So whatever current that flows out will flow split into this branch and this branch. So it's basically two branches that are parallel. So, right, so ZTH is basically minus J8 parallel with 8 plus J8. Okay, so that's the I think important part. As long as you can see that, then the rest is just maths. Okay, so minus J8 plus minus. Okay, so the rest, okay, all the step by step, I think you can sort of see. All right, important thing is just this first step. Okay, as long as you can see how I derive the Thevenin's resistance, which is the same way as how you do a DC circuit, then the rest is just dealing with the complex number part. Okay, question 11. Find the current I using phasors and impedance. Okay, so we are given this. So this here we have two branches that are parallel. Okay, so the first thing is you want to compute the equivalent impedance, correct? So we have this. So this is 2.3K, 1.1K, and I want to convert the equivalent impedance. Okay, so this would be ZL. So ZL would be J omega L. So that would be J omega in this case is given 3,190 milli, which will give me J570. So this would be J570, and ZC is 1 over J omega C, which will be minus J over 3,055 nano. It should be minus J6061. Okay, so to find the total current I is the same, V over Z. So I need to find a total impedance. So the total impedance would be the parallel of the two branches. So the first branch would be 2.3K, which is 2,300 plus the J570. Okay, parallel with the second branch, which is 1.1K minus J6061. Okay, so it is the same as before. So it is multiplied over the addition. So it's 2300 plus J570. Okay, multiply by then. Okay, so the rest of it, I will leave it out. We go to the answer here. Okay, so that is the final answer here. And once you get this, then you put it back into the formula, right? V by Z, which will be, so the V is 636, okay, with a phase angle of pi by 12. Okay, so it will be 636 angle 15 degrees over 2260. Okay, so that will give me 0.281 angle degrees. Okay, so this is again in the phasor form, so you need to express it in the time domain form, which would be 0.281 cosine 3000 t plus 22.56 degrees. Okay, so it's just the complex part only. Okay, it's only the complex part that is the sort of the tedious, steps involved. Okay, but the rest of it is the same. Okay, so here find the voltage VT. Okay, so to find the voltage VT, we know that the current that flows in. Okay, so current times impedance, correct? I times ZT will give me the total voltage. So again, I need to do all those steps involved. So the first thing is you convert it to two equivalent impedance. All right, so you have your V over here, and you can convert it to Z1 and Z2. Okay, so Z1 will be 2 plus J omega L. So omega in this case is 300, and 0.01 should give me 2 plus J3, and Z2 will be 3 plus 1 over J omega C is 1000 micro. So that will give me 3 minus J 10 over 3. Okay, and since they are both parallel, okay, then you can do the parallel formula. So Z total Z is Z1 parallel with Z2. Okay, so that will give me, okay, so again you do the same way as you do with resistors. Okay, that will give me 3.23 angle 12.1 degree. Okay, and with that you can calculate your V. Correct, because V is IZ, which will be so the current is already given to us 10 cos 300 and T. That means it is 10 angle 0 degrees multiplied by this 3.23 angle 12.1 degrees. So it will be 32.31 degrees. Okay, which means you can now rewrite it as 32.3 cosine 300 T plus 12.1 degrees. Okay, and then finally they ask for the current IC. Okay, so this is, you can use, I mean, there's different ways to do it, correct? You can use current divider rule since you got the current coming in, or since you already calculate V, you can take V divided by Z2, you can also find IC, correct? So you can use either way. All right, so if you use the current divider rule, then you will say Z1 over Z1 plus Z2 multiplied by I, which will be 2 plus J3 multiplied by 10 over 2 plus J3 plus 3 minus 10 over 3 J multiplied by I. I is 10. Okay, so that will give me 7.2. Okay, so all the detailed sort of complex number part, I will leave it to you to go through that. I think it's just quite tedious, but should be doable. Okay, just need to do step by step. Okay, so if you look at the whole AC analysis part, all right, it is nothing new. Okay, in terms of the concept, all right, it's the same DC concept. Only thing is the introduction of the complex numbers inside. Okay, since we are dealing with capacitors and inductors. Okay, other than that, everything else is the same. The Thevenins, the current divider rule, voltage divider rule, all are the same. Okay, so that sort of brings us to the end of the tutorial questions. Yeah, so I would say that I think it's not that difficult. If you look at the DC part, as long as you understand the behavior of capacitor and inductor in steady state, and how to apply the transient formulas, then that part I think you should be confident. And in the AC part, as long as you know how to apply the same DC analysis rules and you get the complex part correct, then it's also easy to solve. Okay, so that wraps up for today's tutorial. Okay, so I think we have already released all the practice questions. Okay, that is based on past year papers. All right, so I would strongly encourage you to go through all those questions yourself. Okay, attempt them. Okay, at least think about how you solve it and how you'll approach it. Okay, of course, if you can time yourself, will also be good. Okay, so you have a sense of how fast you can solve these questions. Okay, sometimes it is not that you can't solve it. Sometimes it's in the moment you make some mistake, then you take longer than you expect. All right, so just have a go at it. All right, when you do the question, just to see how fast you can solve those questions. Okay, are there anywhere else you can access past year papers? I think the only other person you can probably ask is you can ask your TAs. Okay, any seniors or TAs that you have contact with in your class, then you can probably ask them to see if they have any other questions they want to share. This tutorial video, I will release the link later. Okay, for you all to have a look. Okay, so I will stay on the line. Okay, if any other questions, you can ask me. If not, I'll see you all on Thursday for the revision. Okay, so the conversion here is a normal. It's just like how you convert any complex number, correct? If I say x plus jy, you convert it to magnitude and phase. Correct? Magnitude is x square plus y square square root, and the angle is inverse tangent of y over x. So it's the same thing over here. Only thing is in our case here, x is your r, and this is your j omega l. So just like how you normally convert any rectangular form to polar form. Yeah, I mean, if you can, are we allowed to get past year paper from the internet? Yeah, I mean, if there's any one who has posted it before and you download that, is fine. Are there any restrictions on the notes? Okay, so there are no restrictions. Okay, so any hard copy material you can bring. Okay, so yeah, don't worry. So on Thursday we will discuss more on the midterm. All right, after we finish the practice questions. Okay, so I'll see you all on Thursday. Okay, bye.